Hi, today I am happy to introduce our work on ParGeo, a library for parallel computational geometry. My name is Yi Qiu. This is work done at MIT with my co-authors Shangdi, Lakshman, Yan, and Julia. ParGeo is a library containing parallel algorithms for computational geometry. Our work is motivated by recent advances in parallel shared memory machines and that most existing libraries in computational geometry are not fully parallel. In this talk, I am going to first introduce the modules in ParGeo, followed by some experimental results. Then I am going to focus on new parallel algorithms for convex hull and smallest enclosing ball. First, I am going to introduce an overview of the modules in ParGeo. The first module is the static and dynamic parallel K-D tree, a well-known spatial indexing data structure. We implement a spatial median multidimensional K-D tree, which is a binary tree that recursively divides the dataset at the spatial median. Our K-D tree supports parallel construction, KN search, and range search. We also have a dynamic K-D tree that supports batch updates. The second module is a spatial graph generator. It contains multiple graph generators that take in multidimensional point datasets and output graph edges. For example, it is able to construct a KN graph, minimum spanning tree, and other graphs as listed. As indicated by the arrows, the K-D tree introduced in the first module is used here for generating KN graph. It is also used for generating beta skeleton. The third module contains implementations for algorithms in computational geometry. They include many algorithms, such as those for a convex hull and the smallest enclosing ball. As indicated by the blue arrows, we use some of the geometry algorithm to generate spatial graphs. The fourth module contains a point data generator. So currently, it supports generating multi-dimensional uniformly distributed points and a clustered data generator. In our benchmark, we show that on a machine with 36 two-way hyper-threaded cores, our library achieves parallel speedups of up to 46 times and on average 22 times. Next, I'm going to briefly talk about our parallelization of the quick hull and the divide-and-conquer method for the convex hull. The convex hull is a classic problem where we find the smallest convex set containing all the input points. The quick hull algorithm proposed by Barbara et al. Is one of the most practical algorithms for this purpose. The algorithm works by incrementally adding exterior vertices to the hull, which form new facets, replacing existing facets underneath, as shown in the example when we try to add point P. The algorithm is not easy to parallelize because concurrent addition of vertices may cause conflicts. We propose a reservation-based parallel algorithm for the quick hull and implement it in 3D. As we can see from the diagram, when we try to add P and Q in parallel, the facets that they replace overlap in the yellow shaded region, causing conflicts. Instead, we let each vertex being processed reserve the facets they want to delete in advance and only let non-conflicting vertices being processed in parallel. We combine this method with a simple divide-and-conquer method, where we divide the data into subsets and compute the subhulls for each subset in parallel. And then we do a final merging computation using the parallel quick hull I just described. The method combining the divide-and-conquer and parallel quick hull is called DC-Inc, represented by the red bar in the plot. It is very fast, as you can see. There's also an even faster method, which we will cover in the paper. Next, we move on to the smallest enclosing ball problem. As the name suggests, the problem is to compute the tightest possible bounding ball given the point dataset. In a nutshell, we propose a sampling improvement over an existing Orson scan algorithm proposed by Larson et al. We first introduced Larson's Orson scan algorithm. So in the 2D example, we first impose a set of axes on the dataset, forming quadrants. Then for each quadrant, we find the furthest point from the origin. An estimate of the smallest enclosing ball is then computed using these points. We repeat the process until all the points are in the ball. We find that repeatedly finding the extremes for the quadrants involves repeatedly scanning the whole dataset, which is very expensive. So instead, we propose an optimized algorithm that finds the extremes only on a subsample of the dataset, which greatly speeds up the process. As we can see from the running time plots, our proposed method achieves the best parallel running time among all the baselines. We have presented the ParGeo library, a library for parallel computational geometry. The link to our open source code can be found here. In the future, we plan to include more algorithms and implementations. We also plan to generalize existing implementations into high-level programming constructs for computational geometry. Thank you for your attention.